Welcome everyone to the first video on chapter 13. We're going to be talking about solutions in these chapters. In this first video, we're going to just kind of define a little bit more about what is a solution and why things dissolve in solution. So, talk about solutions, right? We're talking about mixtures of things, right? Solutions are mixtures of compounds, right? A homogeneous mixture typically is what makes up a solution, right? So we can talk about mixtures first in gas phase, okay? For gases to mix, as the example at the bottom of the slide here, right? If I want to mix together, this oxygen and argon gas are separated or remove the barrier, right? They will naturally mix together, and that mixing is due to a term called entropy, okay, it's related with disorder and things like that. And we'll discuss that more later in the semester in these sets of lecture videos when we talk about thermochemistry, okay. But for now, just talk about the idea that things want to mix, things want to be mixed, be more disordered, disorganized, and the energy that's related with that desire to be more mixed is referred to as entropy, okay? And so that's in gases, that's what dominates the mixture. Now in solutions, there's this entropy, this wanting to be have this disorder that exists, but more prevalent are the interactions between the molecules in solution, right? Because in gas phase, things are bouncing around, they're a lot further separated from each other. But in solution, everything's right next to each other. And so these intermolecular forces that we talked about in chapter 12 are going to play a much more significant role as to whether or not things mix together in solution. Okay? So, remind ourselves some terms that we'll be using when we talk about solutions, right? We'll talk about the solute, solvent, and the solution. Okay? A solution, right, is a homogeneous mixture of two or more substances. In this solution, right, there's the solute, which is dispersed uniformly in the solvent. Okay, typically there's a lot less of the solute, a lot more of the solvent, right? In most solutions we talk about in this class and involved in chemistry, right, the solvent is often water, right, and the solute is then something that's dissolved in water. But the solvent could be other compounds as well. Okay. And so the question we have, right, is in gas phases, right, there's this entropy, this desire to mix that is why gases mix, okay? But in solutions, right, why would something dissolve in a solvent, right? Why would our solute mix homogeneously within the solvent instead of staying separated from each other? Okay, and the reason this is due to intermolecular forces. Right. So we talked about intermolecular forces for pure compounds, right? What's the intermolecular force between two water molecules, between two carbon monoxide molecules, and things of that nature, right? But when we're talking about solutions, we also need to consider the solute-solvent intermolecular forces, right? So for example here, right, I have examples of different types of solute-solvent intermolecular forces. Just like our intermolecular forces we talked before, right? There's dispersion, dipole-dipole, hydrogen bonding, and ion dipole, right? And the different examples here, right? You got heptane and pentane have dispersion interactions between the solute-solvent, right? Acetone with chloroform, you have dipole-dipole solvent-solute interactions, right? Hydrogen bonding occurs between things like ethanol and water, right? And then say like sodium and chloride ions dissolved in water will have ion dipole type intermolecular forces that occur between the solute and solvent. Okay. And so as talked about in that previous slide, right, the intermolecular forces between sodium and chloride and the surrounding water molecules are these ion dipole forces. Okay. Now the process in which salt, sodium chloride dissolves in water gets surrounded by solvent molecules, right? Or more generally, right, when a solute becomes surrounded by solvent molecules, it is called solvation. Okay, Specifically, when the solvent is water, we call it hydration, right? So if you want to hydrate some compound, right, if something goes under hydration, right, it's that compound is breaking apart and dissolving in water and being surrounded by water molecules. Okay. So let's look more in detail as to how, say, sodium chloride would dissolve in water. Okay, right? You go from solid sodium chloride to this aqueous sodium ions and chloride ions, right, where these ions are surrounded by water molecules. Okay, so in this picture, right, if I drop some amount of sodium chloride in my water, right, it first exists as a solid, right, but what happens is there are forces between the sodium ions and the chloride ions, right? These forces are ionic bonding between these two ions, right? Sodium chloride. There's also intermolecular forces between the waters, right? Hydrogen bonding. Okay. Well, in solution, what happens is there's also the intermolecular forces between the water and the sodium and chloride. And what happens is these ion dipole forces that exist between different chloride ions and sodium ions in solution, right, kind of emphasized in these larger pictures, right, these intermolecular forces are strong enough to where the waters can pull off chloride ions and sodium ions into solution and hydrate those ions, right, to then form these fully hydrated ions in solution, right, and these completely dissolved sodium chloride in solution. Okay. Right, and why do things dissolve in other compounds? Well, the main reason is because of these intermolecular forces and strengths of these intermolecular forces. And we often use this term, like dissolves like. Okay, that means that if you have things with permanent charges, they're going to often dissolve in very polar solvents, right? Polar solvents are things that have dipole-dipole interactions, hydrogen bonding interactions, things like that, that can have these ion dipole and hydrogen bonding dipole-dipole type interactions with each other between solute and solvent. Okay, non-polar compounds are compounds that just have dispersion interactions. Okay, so often we refer to solvents as being polar and non-polar. Polar are solvents that again can have dipole-dipole, hydrogen bonding, and ion dipole type interactions, and non-polar solvents are those like hexane or pentane or things like that, that just have dispersion in intermolecular forces. Okay? And so why is it, right, that like dissolves like, right? Why do we want similar intermolecular forces between the solute and the solvent, okay? And the reason is, right, in order to dissolve your solute in your solvent, right, you need to pull apart the solute molecules and you need to pull apart the solvent molecules, right? If I have a bunch of solvent molecules all together, right, and I want to put those in a solution, a bunch of solvent molecules, right, that are all together as well, okay, first thing I need to do is I need to separate these guys, right? I need to create space for them to mix. So these things have to separate from each other. Now, it doesn't necessarily occur exactly like this in real time, right? But these things have to separate from each other, right? And once they separate, then they can mix together, right? And I can then start to get a mixture of solute and solvent particles together, right? And those mixtures, right? And so for this process to happen, right, I need to break these intermolecular forces, these attractive interactions between solute molecules in themselves and solvent molecules in themselves, and then I bring those things together, right? And so it's going to take a lot of energy to break these things apart, and I need to get that energy back somehow. And I get that energy back by favorable intermolecular interactions between our solute and our solvent particles, right? So I need my solute and solvent to have strong intermolecular interactions with each other, and those intermolecular forces need to be similar to the solute and solvent intermolecular forces in order for things to kind of balance out, right? I got to break apart some forces, and I'm going to bring things together, right? And so if it takes more energy to break them apart than the energy I get back when I put them together, then they're not going to necessarily want to break apart, right? And so that is why like dissolves alike, why we need similar compounds, right, or similar intermolecular forces between our solute and solvent molecules in order for things to dissolve very easily in solution. Okay.